Hi everyone. Today I'm going to discuss some properties of tangents and secants of a circle. I'll be introducing also some theorems related to tangents and secants of a circle. But before we proceed to that, let us recall some of these terms which are needed in our discussion. So when we say right triangle, a right triangle has one right angle. So the other two angles, the measure of the other two angles sum up to 90 degrees. Now, as regards to the Pythagorean theorem, so it says that the square of the longest side of a right triangle equals the sum of the squares of the other two sides. So we can work on this theorem as we work or solve for the missing side of a right triangle. So we will be using circle A here with line B, and then line C here, then FG, and we have DE here. Now, in line circle, lines D and C are tangent lines of circle A. And line DE here and line FG are the secant lines of circle A. So when we say line, or when we say tangent line, a line is tangent to a circle if it touches or intersects the circle at exactly one point. And we call the point of intersection as the point of tangency. So take note that line B and line C intersect at point B and point C respectively. So point B and C are called as the points of tangency. Now, on the other hand, a line is a secant to a circle if it intersects at 2 points. Okay, so we'll work on some properties of tangents and secant. First, we have tangent radius theorem. Now, a tangent to a circle is perpendicular to the radius of the same circle that passes through the point of tangency. If we have line B here and point B as the point of tangency, and this is circle A, so we can say that AB is perpendicular to line B. Okay. Now, as regards to the length, no. So from point A to any point on the tangent line, the shortest side is considered as perpendicular to the tangent line. So if we're going to draw another line segment connecting point A to any point of line B, for example, we assign this as point, this is like, let's say this is point D, and we connect this with A here, okay? We have this. And take note that if this is point C, take note that AC is congruent to AB, because AC and AB are radii of the same circle A and they are congruent. So we can say that from the addition segment postulate, we can say that AD equals AC plus CD. Okay, so we can say that AD is greater than AB. So we can really say that the shortest side or the shortest side connecting the center and any point on the tangent line is perpendicular to the tangent line itself. And we can say that AB is the radius of the circle. So as regards to tangent radius theorem, so it says here that a line tangent to the circle must be perpendicular to the radius of the same circle that passes through the point of tangency. So in here, we have the tangent-chord angle theorem. So the tangent-chord angle theorem states that the measure of the angle between a tangent and a chord is half of the measure of its intercepted arc. Looking at the illustration here, we have circle O with chord AB. Take note that AB is just a chord. This is not a diameter since it does not pass through circle O. And this has segment BC at segment BC is tangent at O at the point of intersection B or at the point of tangency B. Now we're going to prove that measure of angle ABC, which is made up of a chord and a tangent line, equals 1/2 of its intercepted arc AB. Okay, so by completing the proof here, so we will try to prove, we're going to prove tangent-chord angle theorem. So for the first statement, we have circle O with chord AB, BC tangent to O at B. So these are the given. And then AO and BO are radii. So we constructed AO and BO. So we can write construction here. And then AO is congruent to BO. The two are congruent because radii of the same circle are congruent. And then angle OBA and angle BAO are congruent. Now, since the two sides here, which are radii of circle O, are congruent, and we have this triangle here, and OB and AO here are sides of this triangle, so we can consider that this triangle is an isosceles triangle. In relation to isosceles triangle, as regards to the angles here, the two angles here are the base angles of this isosceles triangle. And when we say base angles, referring to isosceles triangle, base angles of an isosceles triangle are congruent. That's why the two angles here are congruent. Now, measure of angle OBA and measure of angle BAO are equal. It's because the two angles are said to be congruent. And this is about definition of congruent angles. Now, measure of angle OBA plus measure of angle BAO plus measure of angle AOB equals 180. So we have to inspect where are these angles. So we have OBA here, this one, and we have angle BAO here, and we have measure of angle AOB here. Now, the three are actually interior angles of triangle AOB. And that equals to 180 because the sum of the interior angles of a triangle equals 180 degrees. Now, from the sixth statement, take note that the other two terms here from the left side were transposed on the other side of the equation, and that is possible through addition property of equality. From the seventh statement, we have this eighth statement. The left side are the same. Look at the last two terms, and this was substituted to twice the measure of angle OBA. In the previous statements, we were able to prove that the two angles here are congruent. If so, then their measures are equal. So we can substitute the measure of angle BAO to the measure of angle OBA. So as a result, we come up with twice the measure of angle OBA. So this is about substitution. Now we have BO is perpendicular to BC. BO is, or OB is the radius of circle O, while BC is the tangent line. The two are perpendicular because the radius here intersects the tangent line at the point of tangency. So this is about tangent radius theorem. Now, angle OBC is a right angle. OBC is a right angle because this is about perpendicularity, no? When two lines are perpendicular, then we are able to create a 90-degree angle. And one of the 90-degree angles, since the two are perpendicular here, is OBC. So we can write here definition of perpendicularity. Now, since OBC is a right angle, then the measure of angle OBC equals 90. So this is about definition of a right angle. We define a right angle measuring 90 degrees, no? And then the measure of OBA plus the measure of angle ABC equals the measure of OBC, okay? Now, take note that this is angle OBC. And inside angle OBC, or OBC is equal to the sum of the two angles here. And this is about angle addition postulate. Now we have the third statement, measure of angle OBA plus measure of angle ABC equals 90. So the two here, the sum of the two equals 90. So whenever we have a pair of angles that equals 90, so this is about definition of complementary angles. Measure of angle OBA equals 90 minus measure of angle ABC. So take note that this was transposed to the right side, and this is about addition property of equality. Now, measure of angle AOB equals 180 less twice quantity 90 minus measure of angle ABC. So here, similar terms may be combined. So here, this was just distributed to the two terms. That's why we got 16 statements. So this is distributive property of multiplication. For 7, so we have measure of angle AOB equals measure of arc AB. So take note that AOB here, you have AOB equals the measure of arc AB, and arc AB is the intercepted arc of angle AOB, and angle AOB is made up of or angle AOB here is a central angle with the intercepted arc AB. So this is about central angle postulate. And then working on the two previous statements here, so we'll come up with twice the measure of angle ABC equals measure of arc AB. Since the left sides here are the same, we consider that the right sides are equal. So we got this one, and this is about transitive property of equality. Now, from this one, we arrive with the last statement wherein we were able to prove that the measure of angle ABC here, which is made up of a chord and a tangent line, equals its intercepted arc, because we have so by multiplying 1/2 on both sides of the equation, we come up with measure of angle ABC equals 1/2 the measure of arc AB. And this is about multiplication property. So really, the measure of an angle, which is made up of a chord and a tangent line, equals 1/2 its intercepted arc. For the double tangent segment theorem, the tangent segments to a circle at external point are congruent. So if we have two tangent lines here intersect at external point A, we can say that the two are congruent. Circle O has tangents AB and AC, and these are given. We have BO and OC are radii of circle O, and this was constructed in the illustration. Angle ABO and angle ACO are right angles because the radius and the tangent line, the radius intersect at the point of tangency from the tangent line. So this is about tangent radius theorem. Triangle ABO and triangle AOC are right angles because each triangle here has a right angle, which are ABO and ACO. And this is about definition of right triangles. AO is the hypotenuse of right triangles ABO and ACO. Since the hypotenuse is opposite the right angles. AO is congruent to AO. This is about reflexive property. BO is congruent to CO because all radii of the same circle are congruent. Now, AO equals AO, BO equals CO because the two line segments are congruent. So this is about definition of congruent segments. Okay, to continue, AO is the longest side, and the square of the longest side equals the sum on the squares of the other sides. And this is about definition of Pythagorean theorem. And we just transpose an expression on the other side, and this is about addition property of equality. So in here, the two are the same. The right side of the equations are equal, so we must conclude that the left side must be equal, and this is about transitive property of equality. Now, squaring both sides of the equation preserves its equality. Meaning, as we extract the square root of both sides, the value will remain the same in AB equals BC. Now, since AB equals BC, since AB and BC are of equal length, then we can say that line segment AB is congruent to line segment BC, and this is about definition of congruent segment. Okay, more on the theorem. So we have the double tangent angle theorem, meaning an angle is composed of two tangent lines. For example, this one, angle 2, So it says here that the measure of the angles between two tangents of a circle is half the difference between the two intercepted arcs. So if we're going to consider angle 2, the measure of angle 2 equals 1/2 on the difference between their intercepted arcs ABC and AC. So when we say tangent-secant angle theorem, so an angle which is made up of a tangent line and a secant line, considering, for example, angle 1. So the measure of this is equal to 1/2 the measure on the difference between their intercepted arcs, BC, AC. Now for tangent secant segment here, so for example, this illustration, so this one will come up with a relationship such that the length of a secant segment, for example here, PB times its external part AP equals the square of the tangent segment. And this is about tangent secant segment. And last one, we have the double secant angle theorem. So we have here an angle 3, or angle 3 is made up of two secant line. So this is equal to 1/2 the difference between their intercepted arcs. So by considering this, we will be able to work on each of these problems. So we are going to work on the missing variable. So this one is considered, so by considering tangent secant segment theorem, so we know that the square of the tangent segment is equal to the product on the length of the secant, which is 16, times its external part 4. So we have x squared here equals 64. Extracting the square root, we have x equals 8 units. So 8 equals 8 units. So this one is the application of double tangent segment theorem, such that whenever two tangent segments intersect at an external point R, so the length of the two are equal. So we have x plus 6 equals 2x minus 3. So we have 6 plus 3 equals 2x minus x. So we can say that x equals 9. But for example, we are curious to know the length of the radius here, OP and OQ. So since this is the radius and this is the tangent line, so we can say that the two are perpendicular and we are able to create a right triangle here. So we can make use of the Pythagorean theorem, which states that the square of its hypotenuse, which is OR, is equal to, so since we know what's the value of x, so we have, and we represent this by the radius R. So the square of the hypotenuse can be denoted by R So by working on the Pythagorean formula, so we have the square of the hypotenuse, which is the longest side, equal to 9. Our x here is 9, then plus r. So we can denote this by r plus 9 equals the square of r and the square of the other side, which is 9 plus 6, 15 squared. So expanding the binomial, we have not r squared plus 18r plus 81 equals r squared plus 225. So we have 18r equals 225 plus 81. So we have 18r equals 144. Dividing both sides by 18, r equals 8. Now, the third illustration here is the application of tangent secant angle theorem. So the measure of angle x here equals 1/2 the difference between their intercepted arcs. So one of the intercepted arcs is, or measures 200. The other one measures this, and this will be obtained by working on the sum of 40 and 200 and subtract it from 360. So we have 120 here. So the measure of angle x equals 1/2 times 80. And then measure of angle X equals 40 degrees. Here, measure of angle X equals 1/2 the difference between the intercepted arcs. So we have 178 less 102. So we have measure of angle X here equals 1/2. 178 less 102. So we have 76 here. So measure of angle X equals 38 degrees. And this is about tangent secant angle theorem. So I hope you're able to understand the discussion